Okay, so main title. Nova Geotechnical Cohesive Damage Model GCDM for forecasting landslide occurrences. Okay. Now, in this presentation, I'm happy to talk motivation and landslide failure mechanisms, current methodologies in forecasting landslides, propose the Nova approach, and discuss ongoing investigations. Can everybody hear me clearly?
Yes, yes.
Okay, great. Now, the first point is about motivation. Okay, nowadays, due to global climate change, okay, the global climate change means bring a lot of the heavy rainfall. The heavy rainfall will bring a lot of flooding, landslides, and engineering slope failure, and so on. So this picture shows a massive landslides problems which destroy the village, destroy the people, destroy the infrastructures like the highways and so on. So in the world, more than 90% landslides are caused by the heavy rainfall. Okay, the heavy rainfall come down, okay, to cause the soil or slope materials saturation. Once the soil or slope material saturates, then cohesion or shear strength reduced. Then under gravity or self-weight driving, then landslides happened. That means the soil or some slope materials above the rock would slide down due to gravity driving force. All right. So generally speaking, the landslide includes translation slides like the picture. And another one is progressive rotational slides. So this is two typical different type of landslides. Okay. So the basic failure mechanism in the landslides is the cohesion lost, okay, between the rock or soil or between weak layer to the hard layer, the cohesion lost or shear strength reduced, okay. So that causes the soil block or weak layer slide down above the hard layers, all right. So this picture shows the basic model, rock soil decohesion model. You can see the soil block slide down above the rock layer due to cohesion lost between the interface between the soil and the rock. All right. So there are so many researchers working in this area. They provide they developed a different approach, which includes physics sensors, okay, like some colleagues, okay, in Chengdu Technology of University and so on, using geotechnical models, using conventional rock fracture mechanics model, using general finite element stress analysis model, using standard cohesive row model, and hydrogeotechnical model, and so on. And also another big branch is about a statistical model, okay. All of these models currently, they have limitations in forecasting rainfall triggered initiation and propagation, especially about the precise location of landslides. So the problem is here, can we forecast the landslides in terms of the weather cost? If the weather cost heavy rainfall come down next week or after next week, can we able to predict this landslides initiation and the location and the potential damage? So if we can do, this will help decision makings and reduce the damage to people, to the infrastructures. Now, I'm happy to talk about the new technologies here, a Nova Geotechnical Cohesive Damage Model, GCDM. So this model has has some here, which is a new continuum cohesive damage element. It is a numerical model technology. It's a new one. It aims to predict multiple crack propagation, okay, which is between the computational damage mechanics area, okay. In the geotechnical area, initiation and propagation of natural and engineering slope failure, okay. We consider it's the shear fracture propagations, okay. Then we can predict multiple crack propagation in layered terrain, okay. Once we build up a layered terrain model, okay. Using this model, which has no singularity problems, we don't need a prepared cracking path. There's no conversion problem, although it is strong nonlinear analysis, okay. And this model is computationally highly efficient and accurate. All right. This is the basic GCDM formula, okay, based on the traditional deformation field. We introduce such the enriched degree freedom A, okay, that will be used to describe the discontinuities. Then together with using shifted heaviside function in the left-hand side and also equivalent damage scale, okay, regarding the strain field, then we can describe the crack propagation and the initiation and so on. Our main contribution is on the development of the fully condensed discrete equilibrium equations, okay. Although we used this enriched degree freedom for the crack propagation, however, in the final, the equilibrium equations, we eliminated this degree freedom into the effective stiffness matrix, okay. But we don't lose the accuracy. That is why this model is highly efficient and accurate, okay. Now, regarding its applications in the geotechnical layered terrain area, see, we can use this as the picture showing here. We can use a different group to simulate a different layer of the materials. See, the lower picture shows one of the models here using GCDM, okay. The top layer could be soil layer, okay. The bottom could be rock layer. In the middle between would be a weak layer, okay. Then we can use a different GCDM material model to simulate its performance, okay. That is the basic idea. And meanwhile, to establish this layered terrain model, we can use such basic modeling technology, okay, according to a geological the service or information or basic data, we can extrude the whole machine layer by layer to get the completed the modeling of the terrains. Okay. Now to describe this slope stability, okay, we can use such geotechnical slope stability parameters, GSSP. Now here, in our model, we introduce this geotechnical cohesive strains, sigma rho, and the geotechnical shear fracture energy, G rho. So their critical value is sigma C and GC. So this is the fundamental to GSSP, okay? However, these slope stability parameters would be affected as a function of the heavy rainfall here. So this heavy rainfall intensity will influence these slope stability parameters because this heavy rainfall will influence the soil saturation. The soil saturation degree Martin will give the sigma C GC reduction. Okay, then we can bring this critical value GCCC, sigma C GC into our new model called soil cohesion separation law, then bring this law into the GCDM-based modeling. Then we can predict the shear fracture as the landslide happens, which location, which layer, and the locations and so on. And also we can predict the shear crack propagation, how far it goes. Yeah, the maximum distance moved or landslides the moved, that would be a potential damage size, okay, on the site. So this picture shows a basic rock soil flux model, okay, using the GCDM. So this is a shows such soil layer and rock base, and the sliding could be in this way. So right hand side is showed GCDM modeling as a mesh. Okay, this picture shows the damage crack propagation from the interface in the vertical interface, then gradually move to the slope interface. Then final picture shows the large deformation with the shear crack. Okay, so this is the propagation of the shear slot. This is the video shows the soil block slide down from the rock, from the above the rock. Okay, the right picture shows the response between the shear force and the shear distance here. All right. Now this is an ongoing investigations. Okay, so currently we are working on the correlating the soil shear strength reduction with the saturation degrees. Okay, this soil saturation degree will be influenced by rainfall intensity, and we are developing geotechnical decohesion framework, which also as a function of the heavy rainfall. And we try to establish the hydrogeotechnical coupling model and the numerical model for the layered terrain with the protrusion technologies to build up the three-dimensional domain for the terrains. And also, we are developing the AI algorithm to analyze the historical data of the landslides happened before to adjust our material parameters. And meanwhile, suggest to build up a network for early warning system and the mitigation system for the decision makings. Anyway, this is a challenging topic. Okay, we have a lot of things to do. This is our mainly limited the points here. Thank you very much for your attention here.